topic we are going to start with is active filters. And filters are basically electronic circuits that are designed to filter out or select or reject some certain frequencies. There are two type of filters that are majorly used. Filters are electronic circuits that are designed to select or reject certain set of frequency or certain single frequencies as well. There are two type of filters that we generally use in our applications. One is passive filter and the other is active filter. The filters that are comprised of the basic components like capacitors, resistors and inductors are passive filters. Passive filters are designed to eliminate or to extract or to select or deselect or reject certain single frequency. On the other hand, active filters can select a range of frequency and they can reject a range of frequency, and active filters are comprised of transistors or op-amps, operational amplifiers. Some major advantages of active filters are no loading problem, and they are also cost effective and they are readily available in the market, and there is no attenuation required for active filters. Active filters are readily applied in digital signal processing signal systems and also in communication system as well. The application of filters are employed in entertainment, medical and electronic industry, and they are also used in power electronic circuits. We categorize active filters into four basic types: low pass, high pass, band pass and band reject filters, and these categories are based on the frequency levels that a filter selects or rejects. Each of these filters can be built by using operation amplifier as an active element, and then obviously we combine for the required gain, we combine it with passive element like resistor and capacitor combination, or resistor inductor combination, maybe RLC combination as well. The critical frequency is a specific point at the frequency graph against the gain of the op-amp. Critical frequency is a point at the gain frequency graph at which the response drops by 3 dB from the maximum gain line. It's the 70.7% of the pass band response of the system. Pass band is the range of frequency that is allowed to pass through the filter. The transition area where from the area between the 70.7% of the gain to the maximum gain, 100% gain, is the transition area. The first type of filter that we are going to discuss is low pass filter. Low pass filter, as the name suggests, is the filter that allows the lower half of the frequency or the lower side of the frequency to pass through it. The region start from 0 Hz to the critical frequency, that is FH in case of low pass filter. 0 to FH is the pass band, and after the FH to infinity is the stop band for the low pass filter. The graph shown is for the ideal filter or ideal op-amp. The ideal op-amp shows an abrupt drop off or abrupt response or step response at the end of the pass band, but in a real system the response does not die down or does not drop down abruptly. For any low pass filter, the cutoff frequency can be calculated using the formula or the equation, that is cutoff frequency is equal to 1 by 2 pi RC, This is the diagram for a very basic RC low pass filter, and in this case the lower frequency will be allowed at the V0, and the higher side of the frequency will be rejected from the filter. This graph shows the real response for a low pass filter. We can see that pass band or the bandwidth is from 0 to cutoff frequency, and up the cutoff frequency is at the -3 dB of the curve, and the signal is dropping down at the rate of -20 dB per decade for the op-amp. 0 dB defines the maximum gain of the system, and FC is the FH in this case is the cutoff frequency for low pass filter. The next type of filter will be high pass filter, or the frequency or the filter that allows the higher side of the frequency band to pass through it. And as we can see in the diagram, that the cutoff frequency will decide the point from where the frequencies will be start passing through the filter, and then it goes on the higher side of the frequency. The lower side of the frequency is not allowed to pass through the filter. For the ideal op-amp, again the response is like a step or abrupt, but in actual the response is a curve. For a high pass filter, the lower cutoff frequency is measured through the equation that is equal to 1 by 2 pi RC, and the diagram shows a basic RC high pass filter in which the higher frequency, higher than the cutoff frequency, will be allowed to pass through the circuit, and that will be available at the V out of the circuit. This curve shows the real response for a basic high pass filter. You can see that curve takes a slope up at the 20 dB per decade towards the positive side, and gain the maximum or 70% of the value at -3 dB, and then goes to the higher level, and at the gain 0 dB gain, and the lower cutoff frequency happens at the -3 dB of the gain, and after that the pass band region is available after FC. The third type of filter is band pass filter. Band pass filter, as the name suggests, that it allows a certain band of frequency to pass through it. The graph shows the band of the frequency that is allowed to pass through the filter. This diagram is for an ideal filter in which both sides of the graph, the rising and the dropping side, is the abrupt step response, but in actual it's not a step response. But we can see that a certain band that limit is defined by the higher cutoff frequency and the lower cutoff frequency. This certain band is allowed to pass through the. This graph shows the real band pass filter response, and we can see the bandwidth that is allowed is defined by the higher cutoff frequency FH minus the lower cutoff frequency, that is FL. The both rising and dropping side are not the step response or not the abrupt response. They take the curve take a certain slope for rising, and then curve take a certain slope for the dropping of the response. The lower cutoff frequency and the higher cutoff frequency occurs at 70% of the gain, or the -3 dB of the gain. The central frequency for the gain 1, or the maximum gain of the band pass filter, the frequency is measured through the equation in which the average of two cutoff frequencies, the FH and FL, is measured and calculated, and FH and FL are measured as per their regular equations, that is 1 over 2 pi RC. The one of the rating factor for a band pass filter is the quality factor. The quality factor is the ratio between the between the central frequency of band pass filter to the total bandwidth of the filter. The last type of filter is band stop filter. Band stop filters are basically opposite of the band pass filter, in which there are two side of frequencies are available to pass through the filters, and a central half is stopped by the filter to get through it. So the lower cutoff frequency will define the first half of the signal that is allowed from the filter, and higher cutoff frequency will decide the higher side of the signal that would be allowed to pass through the filter. FL will be measured as per regular equation of lower cutoff frequency, and FH will be measured as per regular equation of higher cutoff frequency. And H minus FL will define the stop band for the frequency, and FL will be starting from 0 to FL, and FH will be going from the higher side of the frequency will be going from FH to the infinity. Again, the ideal graph shows the step response or the abrupt dropping and rising of the signal, but in actual the response doesn't take a abrupt shape, or doesn't drop, or doesn't rise abruptly. It is the band of the frequency that is going to be rejected, or that is going to be stopped from the filter. The lower band will start dropping from minus 3 dB, and the higher band will be will start from the minus 3 dB of the gain.